Here's something that'll make you question everything about modern heating. Engineers in the 1940s could heat an entire drafty farmhouse with less fuel than we use today to heat a single insulated bedroom. And no, it wasn't better radiators or magical boilers. It was something far more fundamental. They understood the physics of heat loss in ways we've somehow forgotten. During World War II, when every ounce of coal mattered and fuel rationing meant the difference between comfort and frostbite, civilian engineers and ordinary families became accidental masters of thermal dynamics. They had to. And what they discovered reveals an uncomfortable truth. We're not heating smarter today. We're just burning more fuel to compensate for ignorance. Today, we're going deep into the physics behind wartime heating efficiency, because understanding why their methods worked teaches us something profound about energy, waste, and the invisible ways heat escapes right under our noses. See, when you look at a 1940s heating system, your first instinct is to dismiss it as primitive. Cast iron radiators, steam pipes, no digital controls. But here's the paradox that energy engineers still study. Those primitive systems often delivered more usable heat per unit of fuel than modern forced air systems do. How's that possible? Because wartime engineers weren't focused on convenience. They were obsessed with preventing thermal waste. Every calorie of heat that didn't warm a human body was a failure they couldn't afford. So they studied heat like it was enemy territory, mapping every escape route, plugging every leak, and forcing thermal energy to work exactly where it was needed. And the principles they discovered, the actual physics of heat movement and loss, those haven't changed. We've just stopped paying attention to them. Let's start with the fundamental physics that wartime engineers understood intuitively. Heat moves in three ways, and each one behaves completely differently. First, there's conduction. This is direct contact heat transfer. When your radiator touches a wall, thermal energy conducts through the metal, into the plaster, through the wood frame, and eventually dissipates into the outside air. Wartime engineers measured this and discovered that unprotected radiators were losing 20 to 30% of their total heat output directly into the structural wall. That's not a guess. That's measured data from field tests conducted in British and American homes during rationing periods. Second, there's convection. This is heat carried by moving air. When air touches a hot radiator, it warms up, becomes less dense, and rises. In an uncontrolled system, that warm air follows the path of least resistance, which is usually straight up the wall, across the ceiling, and out through the attic. Wartime studies showed that without intervention, up to 40% of a radiator's convective heat could be lost to structural pathways instead of warming the living space. Again, this isn't theory. This is measured thermal imaging data from the era. Third, there's radiation. This is electromagnetic thermal energy, the kind you feel when you stand near a fire, even though the air around you is cold. Every hot surface radiates thermal energy in all directions. A radiator facing a cold wall is beaming a massive amount of infrared radiation directly into that wall, where it's absorbed and conducted away. Wartime engineers discovered that reflective surfaces could redirect this radiation back into the room with extraordinary efficiency. The physics is identical to how a mirror reflects light, except we're dealing with infrared wavelengths instead of visible ones.
Now here's where the physics gets fascinating. When thermal radiation hits a reflective metallic surface, particularly aluminum or polished tin, something like 90 to 95% of that energy bounces back. This isn't speculation. This is measurable, repeatable physics. The reflectivity of polished aluminum in the infrared spectrum is well documented. During the war, British researchers tested this principle extensively because aluminum was being diverted to aircraft production. They needed to know if cheaper alternatives like tin plate or even polished steel would work. The answer was yes, though with slightly lower efficiency. What they discovered was that the effectiveness depended on three critical factors. First, the reflective surface needed to be as close to the radiator as practical without touching it. Too far away and you lose efficiency. Too close and you risk heat damage to the material. The sweet spot they identified was about 1 to 2 inches of air gap. Second, the surface needed to cover the full area behind the radiator. Partial coverage helped, but complete coverage was dramatically more effective. Third, the reflective material needed to stay clean. Dust, oxidation, and grime reduce reflectivity. A surface that starts at 90% reflective can drop to 60 or 70% after a season of neglect. But here's the insight that changes everything. This principle applies to any radiant heat source. Wood stoves, potbelly heaters, even modern electric radiators. If the heat source is radiating thermal energy in directions where it doesn't benefit you, a reflective barrier reclaims that energy. Wartime families understood this instinctively because they couldn't afford waste. We've forgotten it because energy is cheap enough that we don't notice the loss.
Now let's talk about the physics of convection control, because this is where wartime engineers got really clever. When warm air rises from a radiator, it creates a convection current. In an unmodified system, that current follows the wall upward because the wall provides the path of least resistance. The warm air hugs the wall, rises to the ceiling, spreads across the ceiling surface, and eventually finds its way to cold spots, cracks, and ventilation pathways where it escapes the building entirely. This is called thermal stratification, and it's one of the biggest sources of heating inefficiency in any structure. Wartime engineers discovered that a simple horizontal barrier placed above the radiator could disrupt this stratification pattern. By installing a shelf or baffle 6 to 10 inches above the radiator surface, they forced the rising warm air to project outward into the room instead of hugging the wall. The physics here involves changing the airflow vector. Instead of vertical movement along the wall, you create a horizontal component that pushes warm air toward the center of the living space. This doesn't require energy. It's purely passive redirection based on physical obstruction. The effectiveness of this method was measured in multiple wartime studies. Adding a properly positioned shelf above a radiator increased room temperature in the central living area by 2 to 4 degrees Fahrenheit with no change in fuel consumption. That might not sound dramatic, but consider what it means. You're extracting 2 to 4 degrees of additional warmth from the exact same amount of fuel simply by controlling where the heat goes. That's free energy reclaimed from waste. In practical terms, that 2 to 4 degree increase could mean the difference between running your heating system for 6 hours versus 8 hours to achieve the same comfort level. Over a winter, that's enormous fuel savings.
But there's another layer of physics that wartime heating systems exploited brilliantly, and it's something modern systems often ignore: thermal mass. Those old cast-iron radiators weren't just heat emitters, they were thermal batteries. Cast iron has high specific heat capacity, which means it takes a lot of energy to heat it up, but once it's hot, it holds that heat for a long time and releases it slowly. This created what engineers call thermal inertia. In practical terms, a cast-iron radiator continues radiating significant heat for 30 to 60 minutes after the boiler shuts off. Modern aluminum or steel panel radiators heat up faster, but they also cool down faster. They lack thermal mass. Wartime heating systems exploited this thermal mass property by operating in cycles. Heat the radiator fully, let it coast on stored thermal energy, then reheat when needed. This cycling reduced fuel consumption because the boiler didn't need to run continuously. The radiator's thermal mass bridged the gaps. Here's where it connects to survival applications and off-grid living. If you're heating with wood, thermal mass is your best friend. A heavy cast iron stove or a masonry heater stores thermal energy during the burn and releases it for hours afterward. You're not just heating air, you're charging a thermal battery. Wartime families understood this because they couldn't afford to keep fires burning all night. They'd load the stove heavily in the evening, let the thermal mass absorb the energy, and coast through the night on stored heat. Modern survivalists and off-grid builders are rediscovering this exact principle because the physics hasn't changed. Now let's address something that wartime engineers considered critical, but modern building codes largely ignore: wall loss coefficients. Every building material has a thermal conductivity rating that describes how quickly it transmits heat. Plaster over wood lath, common in pre-war construction, has a specific conductivity. Modern drywall over fiberglass insulation has a different one. But here's the key insight. No matter what your wall is made of, placing a heat source directly against it creates a thermal bridge where heat conducts rapidly from the hot surface to the cold exterior. Wartime studies quantified this precisely. A radiator mounted flush against an exterior wall without any reflective barrier was losing measured percentages of its output through conduction and radiation directly into the wall structure. The colder the exterior temperature, the worse the loss. On a night when it's 20 degrees outside and 70 inside, that 50-degree temperature differential is driving heat through the wall aggressively. A reflective barrier doesn't eliminate this loss entirely, but it cuts it dramatically by bouncing radiant energy back and creating an air gap that reduces conduction. The modern implication is profound. If you're heating with electricity, which is expensive, every watt lost to wall absorption is money disappearing into structure instead of warming people. If you're off-grid and heating with wood, every log burned to heat a wall instead of a room is wasted labor. Understanding the physics of wall loss lets you intervene intelligently, and the intervention is cheap. Reflective foil, aluminum flashing, even polished metal sheets cost almost nothing compared to the energy they save over a heating season.
Here's why this physics matters beyond old radiators. The principles we've discussed, reflective barriers, convection control, thermal mass, wall loss management, these apply to every heat source. If you're using a wood stove, placing reflective panels on the walls behind and beside it reclaims radiant heat that would otherwise soak into structure. If you're using portable electric heaters, positioning them away from exterior walls and adding reflective backing increases efficiency. If you're in a survival situation with a makeshift heater, understanding these principles means you can extract maximum warmth from minimal fuel. Wartime engineers weren't geniuses. They were ordinary people forced to think carefully about physics because resources were constrained. They couldn't waste fuel, so they couldn't afford to ignore heat loss. We can waste fuel, so we do, constantly, without even noticing. But the knowledge they developed remains completely valid. Heat still moves by conduction, convection, and radiation. Reflective surfaces still bounce infrared energy. Thermal mass still stores heat. Airflow can still be directed. None of this requires modern technology or exotic materials. It requires understanding and attention. So what does all of this mean for us today? It means that before we buy more efficient furnaces or install smart thermostats, maybe we should learn what wartime engineers already knew about heat. That efficiency isn't about burning fuel better, it's about wasting less of the heat you generate. That a sheet of reflective material and a wooden shelf can reclaim more energy than $1,000 worth of new equipment. That physics doesn't care about era or technology, it just works. Consistently, predictably, the same way it worked in 1943 and the same way it'll work in your home tonight. The wartime heating hack succeeded because it respected the physics of thermal energy, and that's a lesson worth remembering. If this deep dive into the science behind forgotten efficiency changed how you think about heat, subscribe to Warfield Survival for more. Because understanding the physics of survival isn't just history, it's knowledge that works forever.